All right, good morning, AngularConnect. Let's just make sure this is hooked up. Perfect. All right, welcome. It's awesome to be kind of on the first talk of the first day here. We haven't even kind of begun to get started with this conference, and I've already run into so many people that I know from our community. So welcome, everybody. For those of you who don't know me, given that Tracy just introduced me, probably all of you do now, my name is Alex Rickabaugh. I'm a member of the Angular framework team, and this is actually my 5th time talking at AngularConnect. I've been here every single iteration since the first conference back in 2015. And so I've been working on the Angular compiler, and that's what I'm here to tell you all about, both how it works in general and some of the cool things that we're doing with it for Ivy. And I've been working on this compiler for almost 2 years now, but I thought it's important to start with the question, why do we have one at all? What is this compiler actually doing? And so I sat down and started brainstorming ideas for what I wanted to show you, and I realized that my own understanding of the compiler and why we have it has changed a lot over the last 2 years I've been working on it. So 2 years ago, Mieszko sat down with me in one of our kind of one-on-one meetings, and he surprised me by asking me how I felt about taking on ownership of the compiler project and getting it ready for Ivy. And I think the word that came into my head at the time was scared. The compiler was this black box to me. It's a different code base than the rest of Angular. I knew vaguely what it did, but I had no idea actually how it worked under the hood. And so today what I want to do is open up that black box and show you a couple of interesting things. I can't go into all the details with the time that I have, but just a few of the different things that you might not expect the compiler to be doing, but that we actually do for you as part of making your app smaller and faster. But why do we have one at all? So the main job of the compiler is to turn the templates you write into the code that runs at runtime. And in Angular, you write your templates declaratively. Right? You specify what you want to happen, the components you want to render, the bindings you want to check, but not how it should happen. You don't describe the mechanisms by which change detection works. Browsers, however, do not understand declarative Angular template syntax. So we have to translate your templates into something the browser can understand. Calls to document create element to actually create the elements in your views, and calls to change detection to actually check, did this binding change from its previous value? Okay, we need to actually go update it. And so you might ask yourself, well, if this imperative code is needed anyway, why don't I just write it and save myself the trouble of going through a compiler entirely? And there's 2 very good reasons why it's worth the trouble. First, writing declarative templates means you deal with a lot less boilerplate. Right? The less you have to think about how something is happening under the hood, how you're doing rendering, the more time you have to focus on your business logic. And secondly, leaving the implementation up to Angular allows us to optimize things a lot for you. So browsers are not a static target. What was fast yesterday may not be as fast tomorrow. And Angular evolves over time to keep up with this and to keep your applications fast. And what allows us to do that is the flexibility of being able to change the implementation on the fly. So as I mentioned, the compiler's job is to take declarative Angular instructions, both your templates and decorators that you write, and translate them into imperative code. So here we have an example component, which is this pop-up panel. It's got a selector, it's got a short little template and an input. And when we feed that to the Angular compiler, it's going to look at this component and generate this imperative code. Right? Here we're calling into the runtime to create a component definition. We're passing some information about the selector, and we're passing this very imperative template function that's calling the Ivy instructions that we've talked about a little bit already. I won't go into any details about how this works at runtime. If you're interested in that, Kara's giving a great talk tomorrow on the subject. So our compiler can do this transformation in one of 2 different ways. The first is what we call just-in-time compilation, or JIT. And this is what used to be development mode in Angular. So when you build an Angular application in JIT mode, you're still taking your TypeScript code and feeding it to a TypeScript compiler, and it gets translated to JavaScript. But all of the Angular decorators that you've written actually end up in that bundled JavaScript, and they run in the browser. And when those decorators execute, they call our compiler, and they translate your templates and your other Angular features into imperative code. The other mode of operation that we have is ahead of time. where instead of running the plain TypeScript compiler on your applications, you run our Angular compiler, NGC. And NGC does the same thing that TypeScript does. It takes your TypeScript code, it translates it to JavaScript. But also, it takes the Angular decorators that you've written in that code, and it precompiles them into the imperative instructions for rendering in the browser. And that way, you don't have to pay the cost of doing that at runtime. So over the next 25 minutes or so, we're going to dig deeper into how the compiler works across 4 different topics. We'll talk about its architecture, right? How it actually, on a macro scale, processes your code. We'll talk about its compilation model, what that is and how it's changing. And we'll look at some of the lesser-known features of the compiler, the things it has to do in the course of compiling your code, including the last big one that we'll take a look at is template type checking, which is one of the most powerful things that we can do. So to understand how the compiler is set up, it helps to kind of know how TypeScript works under the hood, because our compiler is based on TypeScripts. So the regular TypeScript compiler has 3 different phases: program creation, type checking, and an emit phase. And the Angular compiler, as I mentioned, is built on top of that, and it uses all 3 of those phases. And additionally, we add 2 of our own, an analysis step and a resolve step. So let's go through these one at a time. Program creation is the process of TypeScript discovering all of the source files it needs to understand your program. And this begins with your tsconfig.json file. From that, TypeScript learns an initial set of TS files that are part of your program. And it looks at the imports of those and discovers more files. They might be in your app, they might be libraries that you imported from node modules. And it looks at their imports and so on, until it's finally seen all of the code it needs to understand the types in your program and check them correctly. And in the Angular compiler, we actually add into this process a little bit by adding some extra files that you didn't necessarily write. And this is why it's possible to import, for example, ng factory files, if you're doing kind of some of the more advanced things in Angular today. The next phase of compilation is exclusive to our compiler, and that's called analysis. And here what we're doing is we're taking the full set of files in your program, and we're looking through all of the classes in them and trying to find ones that are decorated with Angular decorators. Right? We're understanding what the parts of your application are, the components, the modules, the services, and the directives. And we find one, we kind of try to understand it a little bit. So if it's a component, we'll parse its template. And during analysis, we're only looking at these classes kind of on a one-by-one basis. So if we see a component, we might not have seen the module for that component yet. So we don't know what module it belongs to. We're just trying to understand them in isolation. And later on, after analysis is complete, after we've seen all of the classes, then we go into the resolve phase. And we look at everything again, but this time in the context of the larger picture. So we look at the component, we know what module it's in. And we can make more global decisions and optimizations based on that. And we can also surface errors related to the structure of your application. Like if you put a pipe in the imports of an ng module, we can tell you that's probably not what you intended. So just like the plain TypeScript compiler, the next thing we do is type checking. So we ask TypeScript to tell us about any errors that might have snuck into your program. And we also report on errors in your Angular templates. And as I mentioned, we'll get into how that works in a bit. And the last phase of compilation, we also share with the plain TypeScript compiler, and that's the emit phase. And during this phase, the TypeScript code gets fed through a series of transformations, and it emerges down the line as down-leveled JavaScript code that's ready to run in your browser. And during this step, as we're emitting JavaScript code for each class, we're also adding to it any of the imperative Angular code that we're generating if that class needs it. So we're adding all the template functions to components and things like that. This is actually the most expensive step in compilation, right? Translating TypeScript code to JavaScript. So those 5 phases describe at a high level what happens every time you invoke the Angular compiler. But every Angular application out there actually depends on running the compiler not just once, but many times. And you might not realize this, but even the very simplest app depends on Angular core, which was compiled with our Angular compiler previously before it was shipped to NPM. And so those multiple compilations work together according to something called our compilation model. So let's look at what this looks like in TypeScript. So in TypeScript, if your project includes a file lib.ts, as you know, the compiler runs and it produces a lib.js file, right? And this JS file has no type information. It's ready to execute in a browser. But you can also ask TypeScript to produce a different file, lib.d.ts. And this is a type declaration file. It doesn't contain any imperative code. You can't execute it. What it does is describe the shape of the types declared in the original file. And this turns out to be pretty important. If you build an application that uses this library, and you import that library from npm, TypeScript needs to know what are the types of the things you're importing, because it needs to check whether you're using them correctly. So to put that another way, what the DTS file is doing is it's carrying information about the types in this library from one compilation to the next. And so in Angular, our compilation model is quite similar. So just like with plain TypeScript, if you take a lib.ts file and compile it, say it has a component in it, for example, you get a JS file out. And the JS file includes the imperative code to run in the browser to render that component. But we also change the DTS file. And we include information about that component that future compilations will need. So any application that uses that component makes use of this information. So we encode inside the generic type of the component definition things like its selector, what its inputs are. And this allows us to do two things. One, it allows the future compiler to make use of this component, but it also makes it really clear that these pieces are part of the component's public API. And if you change them, the DTS file will change, and that probably means you need a new, breaking change for your library. So that means when we build an application that uses this library, the compiler knows, looking at this template, that this useful component is actually an instance of this thing that came from the library because it sees the information in the libdts file. So now we're ready to dive a little bit deeper into some of the things that the compiler actually does in the course of building your applications and libraries. And I picked a couple different features that I want to talk about that I think you'll find interesting. We're going to talk about ng module scopes and what they are. We'll talk about this thing called partial evaluation. And finally, we'll go into some detail about how we actually check the types of expressions within your templates. So, ng module scopes, right? What are these things? Well, we're all pretty familiar with referencing components and templates. So here we're using a user view component, but you might not realize that it's actually really tricky for Angular to associate the HTML element that you've written in your template with the component class that's somewhere in a library that you're importing. And that's because you, as a user, never actually wrote an import of this component. You only wrote an HTML element that happened to match its selector, right? And there could have been many components which match this selector. It's not likely, but it can happen. So how did Angular know which component you actually meant here? So if you've used Angular much, you probably know the answer. It all depends on the ng modules. So here we have a pretty simple arrangement with the module declaring two components. And this problem is relatively easy to solve. So because the application component is declared in the app module, all of the components declared in the app module are usable in its template. And we call that set of components the module's compilation scope. So the compilation scope here has both the app component and the user view component. But the picture can quickly get a little more complicated. So here's a slightly more complicated version where we've extracted the user view component into its own module, right? And not only does this module declare it, it also exports it. And that gives the module something we call an export scope, right, in addition to its compilation scope. This is the set of components that this module makes available to any module that happens to import it. So I've used a green arrow here for export, as opposed to a red arrow for declaration. So in this case, the app module's compilation scope includes both the single component that it declares, which is the app component, and the export scope of all the modules that it imports. So in this case, the user view component via the user module. So by building this graph of module compilation and export scopes, the compiler is eventually able to figure out that this user view element that you wrote in the app component template can only be a reference to the user view component class, and it can generate code accordingly. And this is actually an optimization that the compiler is doing to help the tree shaker. We're looking at the template and figuring out, of all of the components in the compilation scope, which ones you're actually using. Because you might have a module that imports all of material, but if you only use the material button, we will only generate a reference to the material button component. And that helps the tree shaker be able to remove things that you aren't actually referencing. And I was actually pretty surprised at how complex it ended up being for the compiler to identify which components are in a template and be able to import them. And until I started working on this optimization, I didn't actually realize that ng modules had these kind of two different dimensions of both compilation and export scopes. So the next part of the compiler is my absolute favorite feature, partial evaluation. Did you know that the Angular compiler contains almost a complete TypeScript interpreter? Right? This is actually pretty crazy. So why would the compiler need to interpret TypeScript code? And the short answer is because we need to know at build time the actual value of certain expressions that you've written in your decorators. So for this ng module, we have declarations and exports. And in order to figure out the compilation scope and the export scope, we need to actually know what the value of these arrays are, which components you're actually referencing. And here, this is pretty easy because both fields are just array literals. We could read the TypeScript code and go, oh yes, this is a reference to one component, this is a reference to another. But this is actual plain TypeScript syntax, and you can do some other things with it. So here's a slightly more complex version. In this version, we've extracted the two components into an array, and we've used this to kind of deduplicate the declarations and exports. And this is a pattern that I see in almost every Angular application that I look at. It's a pretty simple refactoring, and it seems very natural to read. But think about what this means for the compiler. Right? It has to not only understand that ng module takes an object, which has the property declarations and the property exports, and that those are arrays, but it now has to be able to follow this reference to a completely different array that's somewhere else in your code and understand what's coming from there. So in order to do this, our compiler will actually attempt to almost run TypeScript code that you've written in your decorators and try to determine for a given expression what its value will be. And while doing this, we do things like follow property accesses, we expand object and array literals, and we can even execute some simple function calls. Right? Think about router module.forRoot. The compiler actually has to run that. And we can use this to understand even more complex things, such as importing a variable from a different file. Right? Thanks to partial evaluation, the compiler will actually evaluate the imports reference here and read the constant in the other module. And this gets really interesting. So here we have, this time the array is in a config object, right? Which is grouping together a couple different things. Not only does it have this module list, the developer here is also trying to calculate the size of the browser's viewport, right? Using document body, scroll width, and height. The problem is that when we're trying to evaluate this code at build time, there is no browser. There is no viewport. There's no document object. So how can we calculate a value for config when half of the things we need to determine it don't exist? And here's what we actually do for this case. We learn that config is an object with two properties, one of which is an array of modules, right? That we can understand. And the other is an object with two properties that we can't understand. And in this case, we return a special indicator type we call a dynamic value that indicates we reached an expression that we couldn't get past. We don't know how to evaluate document body scroll width. And this has two benefits. The first is that we can make use of the information we do know, right? We can still use the modules array anywhere we want to. And the second, we can give you a really nice error message and tell you when we encountered something we couldn't understand dynamically. And this is one thing the previous compiler for Angular tended to struggle at. you would get error messages that your metadata was not correct or something, and they were a little hard to figure out. So here what the user's doing is trying to use this viewport size in an inline style sheet. And the problem is the compiler needs to know the style sheet string here because it needs to add style encapsulation. So this doesn't actually work. And what the partial evaluator will do is see, oh yes, your styles property here is an array of one value that we couldn't figure out because it took as an input another value that we couldn't figure out. And we should be able to use this to give you a really nice error message. This is something we're working on. So now we get to our last and final topic, which is template type checking. This is a pretty large and complex feature in the compiler, and we're going to look at it from a couple different angles. I think it's important to start talking about what the problem is that we're trying to solve. So here's a fairly simple Angular template. We have one component, we have one binding, and a slightly complex expression with an async pipe. And even in this pretty simple template, there's a lot that needs to be correct at runtime for this to work. Firstly, account view here should be a component, right, with an input called account. The getAccount function not only needs to exist, but it has to take the right parameters of the right types, and it has to return either a promise or observable because we're going to pass it to the async pipe. And whatever this user thing is, it better have an ID property because we're trying to read it. And lastly, you might not realize that the async pipe will actually return null before it gets any actual values. So the account input had better accept null as a possible value. And so there's some significant challenges to being able to type check templates. First of all, templates are HTML. They're not written in TypeScript. Right? The TypeScript compiler doesn't support checking HTML. And secondly, while Angular template syntax and TypeScript look similar, they're actually different languages. So Angular syntax, for example, has null-safe navigation, where TypeScript does not. And the TypeScript compiler just really isn't set up for people to be able to ask it arbitrary type checking questions. So the way we've made this work is actually really cool. The first thing we do is transform all of your templates and all the expressions in them into blocks of TypeScript code that we call type check blocks. And we never emit this code as JavaScript. You never see it as a user, right? We're never going to run it in the browser. They exist so we can feed them to the TypeScript compiler and have the TypeScript compiler give us back errors. And then we present you those errors in the context of your template. So let's build one of these things, right? Here's what the start of it looks like. This one is going to be checking the app component, which has this template. And it takes one argument, this context variable, and any expressions that refer to properties of the app component, we can read off of this context variable. And next, we're going to declare two variables. The first is an instance of our account view component. The second is an instance of the async pipe, and we'll need both of these to be able to check this binding. Note that neither variable has a value, right? And that's okay, because we only care about the types here. We're never actually going to try to run this code. So next, we express the binding itself as a write to the account property on the component, right? And if this property doesn't exist, TypeScript is going to yell at us. And finally, we convert the expression into a pipe.transform call of a call to getAccount. And again, if any part of the types here don't line up, TypeScript is going to let us know. And so if you take this code and feed it to the TypeScript compiler, you might get back an error like this, right? Component.account is not an actual property. Or it might tell you that user ID is the wrong type for the getAccount method. So we're getting the kinds of error messages that we want. But there's a problem. TypeScript is showing us to them in the context of this random code that we generated, which is not helpful to you as developers because you never wrote this code. It'd be much better to show you the error as coming from your actual template. Right? And you might imagine that what we'd want to do is somehow generate source maps for this code that we're generating, and then feed that to TypeScript and have it give us back the error, just like we do with JavaScript. But unfortunately, TypeScript doesn't support this. So we use kind of a really clever trick instead. So here's a simplified example of what we actually feed to the browser, to TypeScript, to check this binding. And in addition to the translated code here, where we've taken your template expression and turned it into TypeScript, you also see we have some comments with numbers. And those are offsets into the template of where we got that expression from. And so now when TypeScript gives us an error, and it says your error is here on this expression, we can look at the comment there and see where that expression came from in the template. And that lets us give you error messages in the context of your actual template HTML. So you can see here there's an error that the user ID in this binding was not of the correct type. But what happens if these templates are in an external file, right? Not in a TypeScript file? In the previous iteration of Angular, the view engine, this was kind of a problem point. You would get error messages that look like this. And if you've dealt with these much, you've probably learned not to trust the line offsets. They can kind of be a little confusing, or things happen to start at the beginning of a line all the time. There's not much indication here of where the problem actually is. We fixed this in Ivy. So now you get an error that's in the context of your template. We show you using TypeScript's really nice diagnostics exactly where the error occurred. And we also give you a pointer that here is the component that's actually referencing this template file. And that makes it much easier to kind of track down these problems. So the last thing that I wanted to talk about with template type checking is support for usage of ng4. And this has been another problem with the old ecosystem where it was not possible under the previous architecture. So suppose our template wants to repeat this account view component for some number of users, right, using an ng4 iteration. How do we go about type checking that? And the reason it's complicated is because the ng4 directive is actually generic. It accepts this type argument, t. And if you think about it, it kind of makes sense. ng4 is going to stamp out a bunch of rows, one for each user. So it has an input that's an array of users, or array of t's, and a generic type for each row. So if we try to write a type check block for this template, we're going to run into some problems right off the bat. First of all, we need to know what the type of this directive is, the ng4 directive. How do we infer its generic type? And secondly, what's the type of the user loop variable, right? To answer the first question, we do something kind of cool. We generate this special function called a type constructor. Again, implementation is not important. It's not actually going to run. What this is doing is allowing us to use type inference to figure out, OK, for a given set of inputs to the ng4 directive, for example, the context users, which is an array of users, what is the generic type going to be, right? And so if context users is an array of users, then the generic type is going to come back as ng4 of user. So the last problem, how we figure out the type of the loop variable, I almost gave up on because it's actually really hard. So the way this user loop variable gets set in ng4 is you call viewContainer ref.createEmbeddedView, and you pass in this context object. And the context object has a $implicit property, and this represents the actual value for each row. And the problem is that this is highly dynamic. Nothing in the ng4 directive says that it has to create rows with the same values as you gave in an array input, right? It can use any value at once for the row. It just happens that ng4 likes to repeat over arrays. So I spent a lot of time thinking about this problem and ranting to teammates. And so I remember one day I was kind of venting to someone when I was banging my head against this and explaining why it was too hard to do. And I said something like, well, honestly, the only way this could actually work is if the ng4 directive would just tell the type checker what type it's going to create for each row. And I thought about that for 10 seconds, and then I was like, well, of course we're going to do that. That's exactly how it should work. So that's what we did. We introduced a static function on ng4 that we ship with Angular Common, and this is called the ngTemplateContext function. And what this does is allow the type checker to ask the ng4 directive what type of row it's going to create. So in this case, it's saying if the ng4 directive is of type ng4 of t, then the type of each row context is going to be ng4 context. And that'll have a $implicit type of t. So now we know that if it's an ng4 of user, that each row is going to be a user. And then it all comes together. We can infer the type of ng4 from its inputs. We ask the directive what it's going to use for each row. And from that row's $implicit, we know the type of the loop variable. And so for the first time in Ivy, we're actually able to type check within an ng4. Right? This was a pretty big kind of blind spot to our type checker beforehand, so I think this is pretty awesome. Yeah. So I wanted to give a quick shout out and heartfelt thank you to 3 amazing contributors who have worked on this stuff along with me and who've been really instrumental in getting both the compiler and NGCC, our compatibility compiler, and template type checking up to standard. So thank you very much, guys. So that's all I have for you. If you've enjoyed this kind of like more technical presentation, I highly recommend you see Mishka's talk later on today about how we make Angular fast, and Kara's talk tomorrow about how the Angular runtime works. So thank you very much, guys.